Assalamualaikum warahmatullahi wabarakatuh. In this video, my team and I will deliver a presentation on memory management, which delves into a critical aspect of computer systems. Memory management plays a crucial role in computer system enabling programs to execute efficiently. Let's dive into the details. The term memory refers to a collection of data in a specific format. It's utilized for storing instructions and processing data. The memory is a big array of collections of words or bytes, each with its own place. The basic purpose of a computer system is to run programs. These programs, along with the data they access, should be executed in the main memory. The CPU retrieves instructions from memory based on the value of the program counter. Memory management is critical for achieving multiprogramming and proper memory use. There are numerous memory management strategies that reflect different approaches, and the effectiveness of each algorithm varies depending on the situation.
We proceed to the next idea, which is why memory management is important. Memory has the same concept and function as our brains, which to store information, and we call it to use later. Then, in order to make that happen, a good memory management is really needed in a system. So, why memory management is important? The first one is because for resource utilization. The memory management will ensure that the user has used memory to maximum state. This will make the memory more efficient in storing data and information at the same time, prevent any unnecessary wastage or leakage. The second one is performance optimization. The memory management will enhance the system performance. This is because the data access time has been reduced and ensuring the availability of required resources. Memory management helps in speeding up the execution of programs and processes. The third one is multitasking support. Memory management is critical in multitasking environments when numerous programs execute at the same time. It allows for seamless switching of context between multiple applications, ensuring that each program has enough memory resources to run. Okay, the second one is three areas of memory management. The primary distinction between L1, L2, and L3 cache memory are capacity and transfer speed. L1 has a little capacity but is incredibly quick. L2 is lower but has greater storage space, and L3 is the slowest of the three, but often has the most storage capacity. Uh, we can observe the pictures below for more information and understanding.
Assalamualaikum warahmatullahi wabarakatuh. I am Muhammad bin NOORAZMAN. Here I am to represent the memory management level. There are three levels. The number one is hardware level, operating system level, and application level. The purpose of hardware level is to manage physical memory and direct data storage. Meanwhile, the operating system level is to provide memory abstraction and protection for processes. Last one is application level. The purpose of application level is to manage memory allocation during runtime for program execution. The component of hardware level is RAM, registers, and memory controllers. Meanwhile, the operating system component is virtual memory, paging, segmentation, and memory tables. And the last one, application level component is heap, stack, dynamic allocation, and garbage collector.
Assalamualaikum. My name is Danish Syafiq bin Abdul Aziz. My matrix number is 083903. So there are four techniques for memory management. The first one is segmentation, which is a process that divided into segments. The second one is swapping, which take process from secondary memory to stored in RAM, which is the main memory. The third one is paging, that divide memory and process. And lastly, compaction, which compact free space of a running system. Let's take a deeper look for each technique. First, segmentation. There are two types of segmentation. The first one is virtual memory segmentation, which divided into a number of segments, but the segmentation is not done all at once. This segmentation may or may not take place at the runtime of the program. The second type is simple segmentation. Each process is divided into a number of segments, all of which are loaded into memory at a runtime, but not necessarily contiguously. I also prepare segment table to show how segmentation maps two-dimensional logical address into one-dimensional physical address. Next, swapping. Swapping technique enables a huge amount of processing to run smoothly even with memory shortage. The purpose is to make a free space for other process. And later on, that process is swapped back to the main memory. Swapping technique play a big role when there is a priority assigned to each process. The process with low priority is swapped out, and the higher priority process is swapped in. After its execution, the lower priority process is again swapped in, and this process is so fast that users will not notice about it. The graphic below illustrates how the process was swapped in and swapped out with each other. Next, paging. The process of paging involves dividing secondary memory into fixed size blocks called pages. Then, the main memory also will be divided, which called frames. Page and frames have equal data size. So, for example, 2 KB for frames, also 2 KB for pages. All processes are begin in secondary memory and will be shifted to main memory when needed. Also, since paging follows no contiguous memory allocation, the pages in the main memory can be stored at different locations in the memory. Last one is compaction, which free space of a running system is compacted to reduce fragmentation problem and improve memory allocation efficiency. Another thing about compaction technique is, it is popular among modern operating systems like Windows, Linux, and macOS. Now, we go to how compaction process work. At the diagram here, imagine black as a used memory, meanwhile white as a free space memory. They will combine together, forming compaction. This process will solve the fragmentation problem, but the drawback is it requires too much CPU time.
Finally, computer memory management is crucial for ensuring that a computer system runs smoothly and efficiently. Memory management system improve application and system performance by controlling memory resource allocation and deallocation. Key techniques such as paging, segmentation, and virtual memory enable the operating system to manage memory resources in a way that maximizes utilization, reduces fragmentation, and delivers a consistent user experience. Efficient memory management also improves system stability by reducing memory overflows that cause crashes and slowdown, as well as ensuring that applications function independently and safely. As a result, good memory management remains a pillar of computer science, critical to meeting the increasing demands of sophisticated software and hardware systems. That is all from us. Thank you for your attention.